Descriptive analytics. Remember that in descriptive analytics, we're trying to describe, using our data, the state of our business, the current situation of our business. One of the ways we do it is by using statistical inference. Statistical inference is the task of making statements of the things you cannot observe. The goal here is to make statements of things we cannot observe directly and be able to characterize our uncertainty. There are ingredients that you need to make sure you have in order to make inference from data. And we'll go through that right now. First, we need to have a population. We need to take out a sample from our population and be able to come up with a data set. Our population is the things we cannot observe. All our data that is out there possible, that is our population. While we collect actual data that we collect, that is our sample. Based on our sample, from our sample population, we take our data set. So the three ingredients that we need in order to be able to do inference is we need to identify the population to which you are making. You need a question, but of course this is of second nature because you know what you want to answer. Once you have identified the population, you can talk coherently about your inference. Secondly, you need to describe the sampling process. You need to tell a story of how your data came to be, or where you collected your data. Where did it come from which population, and how it ended up with you. If you cannot describe your data, then you won't be able to make an inference. So the better you describe, the stronger your results. Once you have that, then you come up with a model for the population. And this is taking into consideration your data set, how elements interact with each other or how they relate to each other, and hence how is your data set related to your population. Let's look at an example. Here we have a population of penguins, and not any kind of penguins. These are penguins that wear hats. So let's say that we have a question and we're trying to answer, is there any relation with the color of hats the penguins use? Or do the color of a hat one penguin uses, does that influence another penguin on using that same color? So first we need to define the population. That's the most important task. And here we say the population is the penguins, but not all penguins, just the penguins that wear hats. Now we need to come up with a sample. So we do the sampling. And the sampling that we do is very easy. The first three penguins that show up, those are our samples. And we see them there highlighted in color. That is our sample. The first three penguins that show up were able to talk with us, gives us our sample and our data set. We start to come up with how do we think they relate to each other. So we see our sample here, the three penguins that showed up. So we come up with a model for our data set. And the model, we say, describes the features that relate to each other and relate to our population. So we can say, well, let's assume that here 1/3 of the population decides to use turquoise hat, and we can see that because we have 1 out of 3. So we can see that there are things that we can assume, and we're assuming that one penguin uses turquoise hat out of 3, or 1/3 of the population. So that's the relation we're trying to assume. The other assumption that we can make is that the hat that the one penguin uses does not influence the color of the hat the other penguin would be using. In other words, they have an independent choice. So looking back at our population, our sample box, we can see our population is all the penguins that were had. We choose a sample, and from that we came up with relationships to make with our data set. And we say that 1/3 of the penguins in the population were turquoise hat. That becomes our model that describes our population. So we see it here. So based on that assumption that we're making, we're saying that 1/3 of our population wears turquoise hat. Now you can see the sample at the bottom left hand corner, and based on our assumption on how we describe the relationship on our data set, then we're making the relation to the population. So we will be saying that the population will look like what is on the right top corner, where 1/3 of the population is wearing turquoise hat. Well, let's assume that when we look at the population in reality, we find that it's not 1/3, but actually, in fact, we see that it's 2 out of 5, or meaning 4 out of the 10 have a turquoise hat. That means that there's a variation. There's a variance from our statistic or assumed value with the reality of the population. So let's look at something very important, describing inference versus probability. So we have a deck of cards here. We have the clubs, we have diamonds, we have hearts, we have spades. The term probability refers to situations in which you know the nature of the system you are working with, and you wish to estimate the probability that the system will produce one or more particular events. In this example of the deck of cards, you know that you're working with a deck of 52 cards, and you have in this deck 13 spades. So if you want to estimate, let's say, the probability that someone would pick or produce 10 spades in the first 13 cards, because you know that the system you're working with is a deck of 52 cards, you will be working with probability. But in contrast, the term inference refers to situations in which you do not know the nature of the system you are dealing with, and you want to infer the nature of the system from the evidence at hand. For example, someone may give you 10 cards or 10 spades in the first 13 cards that were selected, and you, not knowing what kind of deck it is, want to estimate how likely it is that the deck has only 13 spades among the 52 cards, or that in fact it has larger proportion of spades. So that explains the difference between inference and probability. Having said that, we want to know, well, we should talk about hypotheses. Well, a hypothesis is an assumption about the outcomes of an experiment. An inference is conclusion drawn based on the observations and prior knowledge. So the hypothesis is usually made before the experiment. If I do this, then this would happen. There is an independent variable which you use when you do something, and then a dependent variable has to do when something is the result. This is what could happen. Inference is based on the observation, concrete, probable. It can include that this happened, you could directly observe it, but you don't know that it happened based on your observations and your prior knowledge. In statistics, a hypothesis is an assumption we make about a population. Parameter such as any quantity or measurement about this population that is fixed and that we can use it as a value to a distribution variable. Typical examples of parameters are the mean or the average of your data that's collected, and the variance. These are things that you normally know and are parameters that are used when making a hypothesis. Now, the thing is, you might ask yourself, why do I need to know about inference? Maybe it's becoming a little bit complicated. Well, the truth is that you probably use these tools in practice already in your work, as seen in some examples here in marketing, production, sales, customer support. For example, you might be asking, what is the mean number of emails that we need to send before someone signs up to our products? Or what is the mean time between the first login of a user and any other event of the product? Now, when we do this, the population here is the customers, of course, because that's what we're dealing with. You could ask a question like, what is the mean time that it takes for a new lead to become a paying customer? The population here would be the leads that we have in our CRM system. And to be able to study these and come up with an inference, we said we make a hypothesis, and a hypothesis is based on the mean. For example, we're talking about the mean or the average of the response time to new tickets, for example, or the population in this case is the tickets we have created so far in our help desk or ticketing system. Now, once we do this assumption, we're making this hypothesis. For us to investigate if our assumption or our hypothesis is correct or incorrect is that we investigated using a technique called hypothesis testing. Hypothesis testing involves drawing inference about two contrasting proportions, each called a hypothesis, and it relates to the value of one or more population parameters. And we set population parameters. An example is an average or the mean, the variance as well. So we have H0, which is the null hypothesis, and H1, which is the alternate hypothesis. The null hypothesis is something that is commonly observed, something that is readily accepted. And the word null does not mean that it's common, that it's negated or that it's not valid. But the idea here is that this is the accepted fact, and we're trying to nullify this accepted fact. In other words, we're trying to say that if we do this test, we can prove that there is an alternate hypothesis. An example would be thinking in the past. In the past, people believed that the world was flat, so this becomes your H0 or your null hypothesis, that the world is flat. The alternate hypothesis that would be that the world is not flat, that it is round, for example. And there's an one of the scientists, Copernicus, which was a mathematician in the 1500s, this mathematician and astronomer, he wanted to propose that the sun was stationary in the center of the universe and the earth revolved around it, and it was in fact round. So what he had to do, he had to disprove the null hypothesis. In other words, reject the null hypothesis. So he had to change people's thinking, and the way to do that is proving that their thinking was wrong. So his alternate hypothesis was the one that he had to prove that was correct, that the world was not flat. When we have sample data, we reject the null hypothesis and conclude that the sample data provides sufficient evidence to support the alternate hypothesis, or we fail to reject the null hypothesis. In other words, we're saying what was the accepted fact is in fact correct, because our sample data does not support the alternate hypothesis. An example of coming up with what would be your null hypothesis and your alternate hypothesis is looking at the legal analogy for hypothesis testing. So in the US legal system, a defendant is innocent until proven guilty. So your H0 or your null hypothesis is that the defendant is innocent. Your alternate hypothesis is that it's guilty. So if the evidence, in this case, the evidence would be your sample data strongly indicates that the defendant is guilty, then we reject the null hypothesis. Note that we do not prove any guilty or innocence. We're just rejecting the null hypothesis if the sample data strongly indicates the defendant is guilty. If it does not, then we fail to prove the null hypothesis. There are steps that we need to take to do hypothesis testing. First, we need to identify the population parameters and formulate the hypothesis to test. Again, the population parameters being the mean, the average, the variance of the sample data. We need to set a level of significance related to the risk of drawing an incorrect conclusion. We need to determine the decision rule on which to base the conclusion, collect the data and collect a test statistic, and apply the decision rule and draw a conclusion. There are three forms in a one sample hypothesis test. One, that the null hypothesis, the parameter is equal to the constant, or the alternate, the parameter is not equal to the constant. Two, that the null hypothesis parameter is less than equal to the constant, or the alternate hypothesis that it's greater than the constant. Three, that the null hypothesis parameter is greater than equal to the constant, or that the alternate hypothesis parameter is less than the constant. If you notice, the equality part of the hypothesis sign is always in the null hypothesis. The one sample hypothesis test, or the one sample t-test, which is called also, is a statistical procedure used to determine whether a sample of observations could have been generated by a process with a specific mean. In this case, we do not know the variance, the actual variance, because we're dealing with a sample of a population. Remember, we're doing a sample test, so that's why it's called a one sample hypothesis test, also known in statistics as the t-test or the t-student test. A little bit background on this. It was a researcher studied two fields to come up with the best type of beers, and so he collected samples on the fields, and he calculated the average and tried to determine what was the difference between the sample data that he collected in one of the fields with the sample data of the other field, and take in consideration the variance, and in that way he was able to come up with a better tasting beer. So that was a little background. Anyway, let's continue. So the one sample hypothesis test, you calculate the sample mean, you calculate the sample standard deviation, then calculate the test statistic, and calculate the probability of observing the test statistic under the null hypothesis. And this value is obtained by comparing to a t-distribution. Now, remember that we say first we have to identify the parameter, and the k parameters that we're going to use is the sample mean, the sample standard deviation, and we're going to determine the decision, and the decision is going to be based on calculating the probability of observing the test statistic under the null hypothesis. So what is a distribution? T-distribution table. I'm gonna present a distribution chart, which is a bell curve. This is a t-distribution, okay? And we're saying that the mean of the sample will fall right here. The variance is all of our data that is away from the mean, spread out from the mean on either side of the average. Where we have a probability of items falling outside, then we have a outside the population average. So the t-values are 0, 1, 2, minus 1, minus 2. When the probability or the t-value is greater than 2, then we say, or greater than negative 2, we say that we reject the null hypothesis. Okay, and we'll look at that more in practice. But this is just a chart for you to see what how a distribution table looks like, and the t-statistics, which is the t-value that we will be calculating from our mean and our standard deviation. To do that, we look at an example using a collected data, and we're doing a one sample test. So we have these technical support response times collected from BTL technical support team, and what they want to know is if they can reduce the response time to the request to less than 25 minutes. So the first thing for us to do is set up our hypothesis. So our null hypothesis would be that our mean response time is greater than equal 25. And the alternate hypothesis would be that the mean response time is less than 25. You can immediately see, as you look at the data there in the screenshot, is that times are 20, 12, 15, 11, 22, and so on. But they want to reduce the time less than 25. So we're saying that based on if we calculate the average, which is or the mean, in using Excel, it would be using equals average on the range of cells, which would be the cells in B4 all the way to the end of the data set. We would have the mean, and we will say the mean, whatever is that, is greater than or equal to 25 or less than 25. We will now test that, okay, using our t-distribution, our t-test. So the other thing that we want to calculate is the standard deviation. So we'll go standard deviation in Excel and then put a range. To find it, okay? Now, before we continue with the equation, let's understand the risk in hypothesis testing. What we risk is drawing an incorrect conclusion. When we do the hypothesis test, there are 4 possible outcomes. One is that the null hypothesis is true and the test correctly fails to reject the null hypothesis. What this is saying is that the null hypothesis, or the accepted fact, was always correct. Remember, with our hypothesis test, we're trying to nullify the null hypothesis. But in this case, our outcome could be that our test correctly failed to reject the null hypothesis. We couldn't nullify the null hypothesis. The second would be the null hypothesis is false and the test correctly rejects the null hypothesis. The third one would be the null hypothesis is true and the test incorrectly rejects the null hypothesis. In other words, it says, okay, your accepted fact is incorrect. That's what our test will do, but in reality, our accepted fact is correct, so we have an error there. And then the fourth one will be the null hypothesis is false and the test incorrectly fails to reject the null hypothesis. Again, another error, because our null hypothesis was incorrect and the test is saying that it's correct, so we have another error. So we have 2 types of errors. Number 3 outcome and number 4 outcomes. Both will give us errors when we do sample hypothesis test. Now, the probability of making the error type 1 would be alpha. The probability of making a type 2 error will be beta. And alpha, we said, is the probability of rejecting the null hypothesis when the null hypothesis is true, and beta is the probability when not rejecting null hypothesis when the null hypothesis is false. The value of alpha can be controlled, and alpha is typically set to 0.01, 0.05, and 0.10. And the value of beta cannot be specified in advance and depends on the value of the unknown population parameter. Now, alpha is the probability that we're going to be controlling. Now, how beta depends on the true population mean. So in the BTL example, we say the null hypothesis, the mean response time is greater than or equal to 25. In the alternate hypothesis would be that the mean response time is less than 25. If the true mean was 15, for example, then the sample mean will most likely be less than 25. If the true mean is 24, then the sample mean may or may not be less than 25. So the further away the true mean is from the hypothesized value, the smaller the value of beta. Because we don't know the true mean. Okay? The test statistic that we'll be computing using the one sample test on a mean would be t, where the standard deviation is not known. When the standard deviation is known, in a population we have a z-score. But in our case, the standard deviation is not known because we're dealing with a sample. So for the sample standard deviation, we do not use this symbol, but we use S for the standard deviation of a population. So taking that formula into consideration, we can compute the test statistics in the BTL example. And so we have 44 customers. When we do the mean or the average, we see that the response time is 21.91. So the average of taking using the formula from Excel, what is the average equals sign average, and the range gives us 21.91. And the sample standard deviation, again using the formula already in Excel, gives us 19.49 minutes. Therefore, the test statistics, or T, will use x bar minus mu from the sample over the standard deviation square root of n, which n is the number of samples in the number of items in the sample. So we have 21.91, which was the mean response time, minus the average of the population, which is, in this case, we're saying that the average is 25, because we're trying to see if we can reduce the response time to less than equal 25, because, sorry, to less than 25, because we're assuming it's greater than equal 25. So 25 would be the assumed mean of the population. So we subtract comparing the two values, which would be the average of our sample minus what is the assumed average of your population, divided by the standard deviation on your sample, because we do not know the deviation of the population, divided by the square root of the number of samples, which is 44. That gives us a t-value of negative 1.05. That means that negative 1.05 for t indicates that the sample mean of 21.91 is 1.05 standard errors below the hypothesized mean of 25. So that p-value gives you 1.05 standard errors below the hypothesized mean of 25. If we have a significant level greater than 2, which we saw in our on our distribution, then we say that we can reject null hypothesis. Let's look at the example. But in this case, So here we have using a two-tailed test, our critical value would be the one here marked. Alpha was the errors that we were looking at. Y divided by 2 is because you are taking, if the probabilities that you were getting was 0.05, then you divide by 2, you have 0.25 and 0.025 on this side, because we're looking at the two-tailed test. So the rejection region would be anything that is outside. In a one-tailed test, the rejection region again will be anything. On that side or anything on this side. So in the BTL example, we want to find the critical value and draw conclusion. So we assign the value of alpha to be 0.05. We know n, the number of samples, equals 44. So the degree of freedom would be n minus 1, which would be 44 minus 1 gives you 43. We know t, which was the test statistics we calculated, to be negative 1.05. And we know the null hypothesis, we said the mean response time greater than or equal to 25, and the alternate hypothesis, the mean response time less than or equal to 25. So the critical value will be calculated by the formula equals t dot inverse and 1 minus alpha, comma n minus 1. Those are the values that it will request. Alpha you said is 0.05, so 1 minus that equals 0.95. N minus 1, which is the degree of freedom, equals 43. So when we calculate that, we get the result of 1.68. So that becomes our critical value, which is the value here that would be for our rejection region, highlighted in color here. So we said t equals 1.05, and it does not fall in the rejection region, meaning it does not fall on this side. So with that, we fail to reject the null hypothesis. Remember, the null hypothesis was what we wanted to reject or fail to reject. In other words, the null hypothesis, which says that the mean response time is greater than or equal to 25. If we reject that, then we're accepting the alternate hypothesis that the response time is less than 25. So even though the sample mean is 21.91, which is below 25, we have too much sampling errors, and we cannot conclude that the true population mean is less than 25 based on our test. Now, the other alternative approach to step 3 of any hypothesis test is using the p-value rather than critical value, which we calculated just now was the critical value and compared that to the t-test. The p-value is the observed significance level. The p-value decision rule is to reject the null hypothesis if the p-value is less than alpha. And that's what I was talking about when I said, okay, this is alpha. So in the BTL example, we have the p-value is the left tail area of the observed test statistics minus 1.05. And to calculate the p-value, you do t.dist, test statistics, the degree of freedom, and you set it to true. So it will be t.dist minus 1.05, 43 for the degrees of freedom, and true gives us 0.1498. Our result is not to reject the null hypothesis because the p-value is not less than alpha, which is in fact is greater than alpha. So the observed sample mean produced a t-statistics of 1.05. We use the t-distribution calculator to find p. This means it gives us 0.1498, and this means that we could expect to find a sample mean of 21.91 or smaller in 15% of our samples, because if you take that to an average, that's 0.15, then 100 gives 15%. If the true population time were 25, those p-value in this analysis is 0.15. Interpreting the results, since the p-value is 0.15 is greater than the significant level of 0.05, we cannot reject the null hypothesis. Okay, so using the p-value, we can do this. Two sample hypothesis tests available in Excel's Analytics tool pack, and we see the type of test, z-test, when you have the known standard deviation, the t-test when you don't know the standard deviation and you use S for the standard deviation of the population instead of the not the population of the sample, sorry. The two sample test for means of the standard deviation is unknown, assumed equal, and pair two sample test for means, the Excel t-test, pair two sample for means, and two sample test for equality of variance, Excel f-test, two sample for variance. These are the tests available in Excel's analysis toolpath. So we have done the one sample test. Now two sample hypothesis test. What we'll be doing here is comparing two sets of data that will be similar. For example, in the purchase order data, we want to set a hypothesis test to determine if the mean lead time for alum sheeting, which would be one supplier, is greater than the mean lead for durable products, which would be another supplier. So we have mu1 and mu2. Those are sample means of one supplier and the next supplier. So we're going to compare two suppliers to determine which one has a greater lead time than the other. So here we set up the hypothesis test, and we say that the supplier 1 mean minus supplier 2 mean is less than or equal to 0, or the alternate, that supplier 1 mean minus supplier 2 mean is greater than 0. Here in the pivot table, where we'll look at the average lead time for other suppliers, we see that the sample mean is 7 for alum sheeting, and the sample mean for X2 bar is 4.92 of durable products. Excel two sample means if we know the population variances, again we use the z-test. If population variances are known, then in most situations we use the t-test to sample assumptions. If the population variance unknown but assumed to be equal, then we use the t-test to sample assuming equal variances. If the test statistics is negative, Excel one-tailed p-value is correct for a lower tail test. For an upper tail test, subtract the reported p-value from 1, and the reverse is true when the test statistics is non-negative. The critical value reported in Excel should be multiplied by -1. So that is just something to be aware. And how we do that is using the data analysis tool pack. We go to data tab, data analysis, and then we select the t-test. We select the variable 1, the range for variable 1, the range for variable 2, and we select here assuming unequal variances. So in the case of variable 1, the range will be for alum sheeting data, and variable 2, durable paradox data. Once we have filled all the fields, we click OK to run. Then we get the results. The result will be of our two sample test. We'll display here. And what we want to look at is the p-value and the t-critical one-tailed value. So here we see that t equals t statistics 3.8 first, 2, the critical value 1.81, and the p-value is 0.0166. There's another test which is called the analysis of variance, and ANOVA for short is used to compare the means of two or more population groups. ANOVA derives its name from the fact that we are analyzing variances in the data, and each of the population groups is assumed to come from a normally distributed population. An example using difference in insurance survey data. The average health insurance satisfaction scores 1 to 5 and by education level. The way we do that using the Excel ANOVA tool, you go to the data tab, the data analysis tool pack, and then you select ANOVA single factor. You select your input range. You put your select if you're gonna have labels in the first row, alpha, which again degrees of errors, and then this is a value set. Then if you want to put the output in the same workbook, in a different workbook, etc., you hit OK, and you get the results for the ANOVA test. Once you run the ANOVA test, this is the result. You will see the summary for the count. You see the average and the variance. On the ANOVA test, you will have the p-value, using the alpha as 5%, we get a p-value of 0.35. Once the value is less than or less than the alpha or greater than equal, you can make your decision. In this case, p-value is equal to 0.356, which is less than 0.05, so we reject the null hypothesis. Okay, and that's it for this lesson. So I hope it was informative.